When two lines are graphed on the same coordinate plane, there are three possible results that can occur. Let's look at each of these possibilities by solving three different systems of linear equations using the graphing method. In our first system, the first equation is 2x minus 4y equals 8, and we'll graph the solutions of this equation using a blue line. Note that because of the way the equation is written, it's easy to graph this line by finding the x and y intercepts. To find the x-intercept, we let y equal 0, and we have the equation 2x equals 8, or x equals 4. Therefore, the x-intercept is the point 4, 0, and we can graph that on our coordinate plane. Now to find the y-intercept, we let x equal 0, and we have negative 4y equals 8, or y equals negative 2. So the y-intercept is the point 0, negative 2, and we will plot that point on the coordinate plane as well. Now we can graph the line by connecting these points. And the blue line contains all the solutions of that equation. Now let's move to the second equation of our system. Y equals negative 2/3 x plus 5. We'll graph this equation with a red line. Note that it's in slope-intercept form, y equals mx plus b, and here the slope is negative 2/3, and the y-intercept would be the point 0, 5. So starting from that y-intercept, we can now find more points on the line using the slope, which is the rise over run. Since the slope is negative, we'll count down 2 units on the y-axis, and then to the right 3 units along the x-axis. Then repeat that process down 2 and to the right 3. And then we can connect these points to form the graph of this second equation in our system. Note that these two lines are intersecting at the point 6, 1. So that point is the only point that falls on both of the lines, and therefore it's the only point that is a solution of both equations simultaneously. So when we have intersecting lines, we see that there is one solution to our system. In this case, that solution is the ordered pair 6, 1. Now let's look at the second possibility with a second example. In this system, the first equation is y equals negative 1/3 x minus 2. We see that it's in slope-intercept form, so we'll move to the y-intercept of 0, negative 2, and then use our slope, negative 1/3, to move down 1 unit on the y-axis, and then to the right 3 units along the x-axis, down 1 and to the right 3. We could also find more points by moving the opposite direction, back to the left 3 and up 1. And then when we connect these points, this blue line will show all the solutions of this first equation in our system. Now to graph the second equation, we could put it into slope-intercept form by isolating y, but it's also pretty easy to identify the x and y intercepts of this equation. If we let y equal 0, we have x equals 6. So the x-intercept of this line is the point 6, 0. And if we let x equal 0, we have 3y equals 6, or y equals 2. And in this case, the y-intercept is the point 0, 2. Now, if we connect these points with a line, we will see that the two lines formed are parallel lines. They don't intersect at any point. When this is the case, when the graph of the two equations in the system leads to parallel lines, we can see that the system has no solutions. Since there are no points that fall on both of the lines, there are no points that make both equations true at the same time, and therefore there are no solutions to this system of two equations. Finally, the third possibility is illustrated by this last example. Our first equation in the system, which again we'll graph in blue, is x minus 2y equals 8. Clearly, if we let y equal 0, the x-intercept would be the point 8, 0 for this equation. And if we let x equal 0, we have negative 2y equals 8, or y equals -4. So our y-intercept is the point 0, -4. And we can connect these 2 points, and we will see the graph of this first line. Let's graph the second line in red, y equals 1/2 x minus 4. Well, our slope is 1/2, and our y-intercept is the point 0, -4, which is actually the same y-intercept we had for our first line. 0, -4, and then using rise over run, we count up along the y-axis 1, and to the right 2 along the x-axis. And we see that we have another point on the same line. And if we continue this, up 1 and over 2, we'll see that every point on the red line is also on the blue line. In fact, if we were to graph the red line, we would have see it's exactly the same as the blue line. That's because these two equations are actually equivalent. If we were to solve that first equation for y and isolate y, we would obtain the second equation. When the two equations in our system are actually the same equation and produce the same line, then we know that our system has an infinite number of solutions. This is because there's an infinite number of points that lie on both of these two lines. So there's an infinite number of ordered pairs that would make both equations true at the same time. Now, it is important to note that having an infinite number of solutions does not mean that this system would have every ordered pair as a solution. For example, if we consider a point that's not on these lines, such as the point 2, 3, if we substitute those coordinates into either one of these two equations, we will see that those coordinates do not make the equation true, since the point does not fall on the line. So there's an infinite number of points that are solutions to the system, but only the points that are on the line are those solutions. Thus, we can see this is the third of our 3 possibilities. To recap, one possibility is we have intersecting lines, in which case there is one solution to our system. The second possibility is parallel lines, in which case there are no solutions. And the third possibility is that both equations actually represent the same line, in which case there are infinite solutions to the system.